Cool. I forgot what my Euclid answers were. Well, I hope I remember. Oh, here we go. Okay, I got it. Okay. So we left off on Wednesday. We didn't finish the lecture. So we left off right here. Well, right before when we quit, we were talking about inverse CDF, and you have to do inverse CDF on the midterm exam on Monday. So good luck as you study. We'll see you guys. Do you guys ever have nightmares where you afraid you slept through your exam or something? So I never had that dream, but I have, now that I'm teaching, I have nightmares that it's exam day and I forgot to make photocopies, and I have to show up to the exam and I don't have papers to pass out, and I'm like, no. Okay, anyway, it's like the reverse. Sorry. Okay, what are we talking about? We're talking about convolutions. Okay, so the idea of a convolution is you get a new random variable by combining other random variables. Okay, so basically you just get a sample of m draws from x. Okay, and so x are all kind of random variables, and then if you add them up, the sum itself is a random variable, right? Because it's, you're adding up random values, so the sum is also going to be random. That's going to have its own distribution, and so that sum is, we call that thing a convolution. And it turns out that a lot of random variables that you deal with can be expressed or turned into convolutions. Right? And this is a quick and easy way to generate a lot of variables that we're familiar with. So one of the simplest is the binomial distribution. Right? You have MIID draws from the Bernoulli. So the Bernoulli is either a 0 or a 1. You get m of these things, or n, whatever letter you're using, right? How many trials are you doing? You do that many. Each of them has a probability of becoming 1 with probability p, 0 with probability 1 minus p, and the sum of those, which is, how many successes did you observe in m trials, or n, is going to be a binomial random variable. So we just say the convolution, the sum of these individual Bernoullis, is a binomial distribution with parameters m for the size and p for the probability. That's simple and straightforward, right? Okay. So if we wanted to do this, right, there is a random binomial function in R, but here's just a very simple function that we could use to generate random binomial, okay? So it will be a function with parameters m and p. This is just going to generate one value of a binomial, okay? So size m trials, probability of success p, and we ask generate m values from the random uniform, m values between 0 and 1, okay? And what we're going to say is basically, if u is less than p, if these mu values, if any of them are less than p, set them equal to 1, right? So this is kind of an if-else, 0 and 1, but basically I started everything off as 0, and then for the ones that are less than p, we assign those to be 1, and then we sum up the x, and that's going to be binomial, right? We could think of probably 100 ways to write this. Some are going to be more elegant than others, but this is fairly simple. No complicated functions here, okay? And then so we have, if we do this, we say give me one value, the first one that pops out happens to be a 6, okay? And we can just say, okay, well, how well does this perform? Okay, so here I'm going to generate 10,000 values. I'm going to use the function replicate which basically takes my function, my random binomial function, and we're going to do 10,000 replicates of this thing. And then we're going to get empirical probabilities based on my 10,000 replicates. So I'm going to take my sample of binomial things, and we're going to just say, how many times did you get 0? How many times did you get 1? How many times did you get 2? How many times did you get 3? And we'll compare that to the theoretic. The theoretic, we can just use d binom. We can just use d binom from R. I mean, we could do it ourselves. 10 choose 0, 0.6 to the 0, 0.4 to the 4, etc., etc. And so we get pretty close alignment, I think. So, we're expecting something around 0.2007 and we get 0.1996. We're expecting 0.2508 and we get 0.2474. And so we get, I think, pretty close alignment between what we expect theoretically versus what we observed empirically. This would just be one random sample of 10,000 observations. Okay? So this is just kind of an alignment check using our eyes. We can also create a graph to produce this, okay? So if you have this is basically a matrix, right? Because I used rbind, and I'm binding empirical and theoretic, okay? So I have a matrix here. You can stick that into bar plot, and if I use beside equals true, then it puts the two bars side by side, and then legend text would be row names with comparison. We could have done this in ggplot as well, but we also see, we get pretty close alignment between the empirical in dark, in black or dark gray, and the theoretic in light gray. Okay, so maybe a little bit of discrepancy. This one, there's a little bit of a difference, but again, there's only a few observations here. So pretty good. Okay. What if we wanted to do something just a tiny bit more rigorous? What kind of statistical test would we use to see if we're observing basically each outcome with the appropriate frequency? Like, am I getting the number 7 as frequently as I should? What's a statistical test we can do? Chi-squared, yeah? Chi-squared, you can check a bunch of kind of categorical outputs simultaneously. So with the chi-squared, you give it basically a table of outcomes along with a vector of probabilities. Now, there's actually a lot of ways you could run the chi-squared test, but this would be the chi-squared goodness of fit test. You're testing to see how good is the fit between your theoretic probabilities and your observed data. So here I'm going to take a table of the sample, which is basically this empirical thing, except it's going to be counts. So basically, each of these things multiplied by 10,000, right? It's the table of the sample. Here I divided by n, and here it's just the empirical is going to be table of the sample without dividing by 10,000. Okay, so it's going to be the counts. So we give a vector of counts, and here we have the vector of theoretic probabilities, which we found back here by using d binom. Okay, and we do a comparison, and then it gives me a warning. It says, warning in chi-squared, the chi-squared approximation may be incorrect. Okay, so I have 10 degrees of freedom because I've got 11 possible outcomes. With 10 trials, we can get anywhere from 0 to 10. So that's 11 possible outcomes. I'm going to have 10 degrees of freedom. And the reason why I'm getting this chi-squared approximation being incorrect is because if we look at basically my theoretic counts, theoretic probabilities, how many times am I expecting to get 0 heads out of 10 flips, right? If the probability of getting heads is 0.6, how many times should I get 0? That's going to happen very infrequently, okay? I'm expecting it to happen less than 1 time, or around 1 time out of 10,000, something around there. And that just number is too small, right? The theoretic probability here is just too small. And so the chi-squared statistic gets thrown off. Anytime you have some cells with very low counts, the chi-squared test doesn't like it. There's technically a central limit theorem assumption based on the counts. And so if any of the expected counts, that would be, the theoretic probability times your number of trials is less than 5, that's where you run into some trouble. So a workaround, okay, so your next homework will, I haven't posted it, right? Okay, no. Your next homework will be posted soon, where you're going to do some random number generation, okay? I should post that so that at least you can see some inverse CDF practice problems, but not necessarily exactly like what you'll see on the exam. So you'll run into this issue in your next homework as well, is that what we have to do, we might have to combine certain cells, right? So here, as far as the outcomes 0 and 1 go, there 0, the expected count is too small. So what I'm going to do is I'm going to combine, we're going to collapse these really tiny categories, okay? So if you have category A, which has a really small expected count, you just kind of combine it with another category. So I'm going to take the 0 category and combine it with the 1 category, okay? Now, this is a named vector where the first value is named 0. So it's a tiny bit confusing. So we have to put quotes. We have to put quotes around the 0, otherwise it's going to, if you try to subset using the integer 0, you get a 0 length vector, which is not what we want. We want to take the cell associated with the name 0. Okay, so we're going to say, all right, give me the counts in cell 0, add them to the counts in cell 1, and we're going to just store that in counts 1. Okay, and then what we'll also do is we'll just delete. We'll end up deleting this. So this 3 gets added into the 12, so now we have the 15 here, and we're going to delete this. Okay, so we're going to collapse these categories, and I only need to do it for this one. Okay, perhaps in your homework you have to collapse multiple cells. Okay, and then we have to do the same thing as far as the theoretic probabilities go. Okay, so as far as the theoretic probabilities go, the first cell in the theoretic probability corresponds to the 0, and the second cell in the theoretic corresponds to the number 1. So I'm going to add those two values, the first and the second, and then we're going to just delete that first cell as well. Okay, so we're basically doing the same thing, except not for the counts, but for the theoretic probabilities. And now I can do the chi-square test between the counts and the theoretic probabilities. I no longer get the warning, and my chi-squared value is 8.6784. Okay? Notice how big of a difference this makes. Okay, when you have, because the calculation of the chi-squared statistic is the observed minus the expected divided by the expected. And so when your expected count is tiny, any deviation from expected is seen as like a huge deviation, okay? And so your chi-squared value can end up getting quite inflated. Here it's 13, and it says, you know what? This chi-squared approximation, it might be wrong, okay? And after we kind of fix that issue of getting rid of these really low probability cells and kind of combining with them others, we get, the chi-squared statistic is quite a bit smaller, 8.674, okay? And so here our p-value is 0.4675, which is bigger than 5%. And so based on this, we have no reason to believe that the data we observed is significantly different from the the expected probabilities as dictated by the theoretic binomial distribution. Let me give you your first view quiz answer. Today's first view quiz answer is the letter E. E as in elephant. E as in elephant. First view quiz answer. All right. Any questions on this? Just kind of generating some values and then doing some statistical tests to see if the random values we generated fit what we expect them to look like. Okay, what about this, right? So the Poisson distribution is used to model kind of the number of occurrences of a random event in a set time frame. So for example, it's the number of pieces of mail received in the day, or maybe the number of injuries that happen in a month, or the number of phone calls you receive at some given time, right? So if you're assuming events happen kind of, or events are uniformly distributed, random uniformly distributed on some interval, then the wait times in between them are exponential, but the number of events within a given time frame follows Poisson. Okay. So, right, so if you think about, so the classic is like, how long do you have to wait at the bank? Waiting time at the bank is exponential. The number of people in line would be Poisson. Okay. The time, right, I guess waiting time between customers, exponential. What about waiting time until, or how long do you have to wait for the fifth customer to arrive? What's that? Gamma, right? So if you say, how much time in between customer arrivals, exponential. How much time until the kth customer, that's gamma. How many people are waiting in line at any given moment would be Poisson. Or how many people arrive within a certain amount of time would be. How many people are waiting at any given moment? Now I'm confused. Is that something different? How many people arrive within a certain time frame is Poisson? What's that? Geometric? Geometric is how many? All right, I gotta review all of these things. But it's all kind of this point process type of thing. Okay, but anyway, we're talking about the Poisson distribution. So what do we get? If x itself is Poisson, the sum of several x values is also Poisson, okay? So if we just say, hey, how many, the number of pieces of mail we expect in a given day, let's say is Poisson with lambda equal to 3, okay? So on average, we expect 3 pieces of mail a day. Some days we get more, some days we get less. Okay, and then we say, hey, how many pieces of mail can we expect for an entire week? For an entire week, that is the sum of however many days the mail gets delivered. Is it 6 days a week? 7, 5? How many days does 6 now? Well, they haven't done Sundays as long as I can remember, but I don't know. Whatever. You take how many days they deliver mail. And you add them up, okay? Or I don't know, should we? Do I add up 6 days or do I add up 7 days? Because I guess it's the generation of mail, is that? So the delivery, now I don't know. Is the generation of mail consistent? Like, does it still happen even though they're not delivering? I don't know, okay. Well, whatever's generating the thing, right? You just add up multiple. Let's just keep it simple. How many pieces of mail will I expect? Monday, Tuesday, Wednesday. 3 days. If each of those are Poisson, I add up Poisson with lambda 3, Poisson with lambda 3, Poisson with lambda 3. The sum of it is going to be Poisson with lambda 9. Okay? So The sum of m Poisson values is also Poisson distributed, but its rate parameter is the sum of the lambdas. The negative binomial distribution, okay? So the geometric distribution is used to model the number x of failures in a sequence of Bernoulli trials before the first success, okay? So for example, what is the probability we have to roll the die 3 times before we get a number 6, right? So if you roll the dice, there's a 1/6 probability of getting the number 6. Okay, what's the probability you roll it? You get a 6 on the very first one. That's the probability of having to roll 0 non-6s. And technically, geometric, there's still a probability of like having to roll it 50 times before you see a 6. Okay, it's a very low probability, but it's not 0, right? Because there's a very small probability that you roll the die 50 times and you didn't get a 6 at all on any of those 50 times. And then finally on the 51st roll, you get a 6, okay? Very low probability, but it's not 0, okay? The negative binomial is kind of like the geometric, except it's used to model the number of failures observed in a sequence of Bernoulli trials before the mth success, right? So how many times do we have to roll x non-6s before we see a 6th for the 3rd time? So how many things do I have to roll before I get my 3rd number 6? Okay? And so the negative binomial distribution can be expressed as a convolution of geometric random variables. Okay? So each one is IID from a geometric distribution, and we would have to do this m times, and then the total number of non-successes, or total number of failures we have to observe before we get our mth success is going to be the sum of those m geometrics. Okay, and that would be negative binomial. I guess I'm out of battery again. This thing eats through batteries. Oh dear. Okay, so this is just another convolution example. Just another classic one. If you've got standard normal variables. So you got z coming from the standard normal distribution, and then you square them, you'll get a chi-squared distribution. And if you do this m times, then that's the chi-squared distribution with m degrees of freedom. Okay. So that's that, right? You draw from the normal distribution, you square it, you do it however many you have. Okay. Gamma distribution, right? So exponential is used to model the amount of time between random events in a Poisson point process. And the gamma distribution can be the amount of time that must pass before the mth occurrence of a random event, right? So we said how much time between customer arrivals, that's exponential. How much time do you have to wait until the 5th customer arrives? That's going to be gamma, and that's basically the sum of m exponential, or 5 exponential values, right? So all you do is you just generate values from the exponential, you do it m times, and then you add them up, and now you have a gamma distribution. So it's kind of just, a lot of these things are, if you know how to do a simple thing and you have the ability to generate randomly, you can generate, more complicated variables. Oops, and I copied and pasted some text. This should say gamma. this has a gamma distribution with shape parameter m and rate parameter lambda. Sorry for the typo. Gamma distribution. Okay, beta distribution. The beta distribution, this is a little bit of an interesting one, okay? So beta distribution has shape parameters A and B, or alpha and beta or whatever, two shape parameters. And this is kind of like you take the sum of A plus B, you generate that many values from an exponential distribution with rate parameter 1. And then you take the first A, that forms your numerator, and then you take the sum of all of them, and that forms your denominator. Okay? And so that way you always get a value between 0 and 1. Okay. This only works if you're using natural numbers for A and B. Technically, the beta distribution does allow for decimal values. You can have shape parameters with decimal values, and it does allow for that. So this convolution would not work for that. But for the natural numbers, if you've got kind of natural number shape parameters, this convolution works. It's a ratio between the sum of the first A and the sum of all of them. Okay, you have A plus B all together. Okay, you can also express it, right? Because the sum of exponentials is basically a gamma distribution. You can also do, you can take two gamma variables, u and v, and then beta will be u divided by u plus v. Okay, and that works there. Okay, and then the last one, which the last convolution we'll look at today, is the t distribution, which is z divided by the square root of v over v, okay? Where v is a chi-squared distribution, which itself is a convolution, and z is a standard normal. These are independent, z and v are independent, and this would give us a t distribution. And I think you probably had to learn some of these relationships for 100b, but we can also just generate them because we know these relationships work. Okay. Let me give you your second view quiz answer. Second view quiz answer today is B. B as in bear. B as in bear. Okay. And now let me introduce rejection sampling. So this is new stuff. So rejection sampling is another method for generating random values from a distribution. So far we've looked at inverse CDF, and we've looked at convolutions, and rejection sampling is another way for us to generate random values, okay? And again, we might use this if we need to generate values from some function that doesn't have a built-in generation function in R. So it's not like R binom or R, one of the values that R already has built in. And then maybe, so if you can use inverse CDF, if you can figure that out without too much trouble, I would recommend that. But there are some instances where you can't use inverse CDF because perhaps the CDF you can't figure out, or the inverse CDF you can't figure out, right? So there's a couple processes for inverse CDF. Is you have to figure out the CDF first, and you have to figure out the inverse CDF. So perhaps you're in a situation where that's either not possible or just hard and you don't want to do it, okay? So if that's the case, then we can do rejection sampling, okay? And even if that's not the case, you can still do rejection sampling. So again, the goal is we want to sample from some function f, okay? And we know the PDF. We know the PDF. So that's requirement number one. You do need to know the PDF, okay? But you don't need to know the CDF. You don't need to know the inverse CDF, okay? So we don't know the CDF. We don't know the inverse CDF. And we aren't able to generate directly from F, okay? There's going to be some similarities between rejection sampling and importance. It's called importance sampling, but kind of that weighted Monte Carlo estimation. There's some similarities, but this is not, rejection sampling is not used to estimate the value of an integral. It's used to generate a sample from some distribution, if you want the actual values themselves. So we're not able to generate from F, so what we do is we generate from a different distribution G, candidate distribution that we are able to sample from. So perhaps you can't sample from some distribution F, but you say, I do know how to generate values from the normal distribution, or I do know how to generate values from the exponential distribution, whatever we want, okay? And much like importance sampling, the support of F must be fully contained inside the support of G. You need to have, if it's possible for F to generate a value, then it also has to be possible for G to generate that value. You can't have G equals 0 in some region where the F is able to generate values. Okay, so that part is also the thing. And then there's also another requirement that there is a finite constant such that m times g of x is greater than or equal to f of x for all x's inside the support. Okay, so an example where this is sometimes violated, right? So if you look at, say, the tail, if you look at the normal distribution, and let's say you look at the t distribution. I don't know how to change my pen color. Okay, so the t distribution, this is exaggerated. Okay, the t distribution just has a much wider tail, right? They both have the same support. They both go from negative infinity to positive infinity, okay? But what is the ratio? Let's say G is, the normal is G, and the t distribution is F, okay? As we go out to infinity, what is the ratio? What number m, what is the number m that you'll have to multiply G by to get F? Infinity, right? As you go out to the tail, G gets like with the t distribution, F has such a, what we call a heavier tail than G, right? So if you just even think of like, can I plot this somewhere? Okay, so if I say, what is d norm of, say, 6 versus d norm, I'm sorry, not d norm, dt of 6 with, say, degrees of freedom equal to 2, okay? What is the ratio between this, right? Okay, like I would have to multiply the density of the normal distribution by 702,000 for it to equal the density of the t distribution. And it just gets worse as you go farther and farther out, okay? So there does have to be a finite constant m, such that if you multiply m times g, whatever distribution you're drawing from, it's going to be greater than or equal to f for everything in the support. So if your target distribution is the is the t distribution, then even though the normal distribution has the same support, it's not going to work for this because there doesn't exist a finite constant m that would work. Okay. So the kind of, if there is a finite constant though, the most efficient choice is to pick m to be the maximum value between the ratio between f and g. Okay? So if you think of, all right, well, what is f divided by g? The most efficient choice would be that value m and nothing any larger, okay? If we pick anything less than m, then m times g is not going to satisfy the condition that it's greater than or equal to f. And anything larger than that would be considered wasteful because m times g is going to be bigger than f, right? So that's what we have. Okay, so this is how rejection sampling is going to work. You just generate a value from G. This is the distribution that we are able to sample from. And then we will calculate what is the target PDF, F, divided by M times G, okay? And so this value is going to be always less than or equal to 1. Okay, because m times g, we've established that when we do m times g, it's always greater than or equal to f. Okay, so f divided by m times g is always going to be less than or equal to 1. So this ratio, or this r, is going to be some value between 0 and 1. And then we generate a separate value, random uniform, between 0 and 1 as well. If the random uniform value is less than r of x, we will accept it. And if the random uniform value is bigger, we're going to end up rejecting this x value that we generated from g. Okay, and if you follow this process, we're going to generate a bunch of values from g. We're only going to keep some of them. And the values that we keep will have the distribution defined by f. Okay? I think it will make a little bit more sense with a picture. Okay? So we're going to say this is our target distribution. The target distribution is the beta distribution 2, 2. Beta 2, 2 distribution. If you go, it's x 6 times x times 1 minus x, okay? If you calculate the beta constant, which is gamma 2 times gamma 2 divided by gamma 4, that comes out to be 6, okay? Or 1 over that thing. You get 6, x times 1 minus x. This is defined on 0, 1. Our candidate distribution will just be the random uniform, which has PDF 1, okay? All right, and its support is compatible. And so this is what the distribution looks like, okay? F has the red line, okay? This is the beta distribution, beta 2, 2 distribution. And our candidate distribution is in orange, okay? And that has PDF equal to 1 for all of this, okay? And so what we're going to do is we're going to multiply G, this is the uniform, which is 1. We're going to multiply G by some constant so that G times the constant is always greater than or equal to the red line. Okay, so we just basically find out the max. I think this is 1.5. Right? So we're going to just multiply G times 1.5. Okay, and so the max choice is going to be, okay, what is the ratio between the best choice is what is the maximum ratio between the red line and the orange, right? So we're going to look at this and we go, okay, it's tallest right here at 1.5 and this is this, right? But we can kind of do it mathematically, right? So here's f, here's g. So we're going to just search for the maximum value of f over g. So we do 6x times 1 minus x is f divided by g, which is just 1, okay? And then we're going to take the derivative of this, set it equal to 0, and solve for where the derivative is equal to 0. And when you solve, you get the derivative equals 0 at x equal to 0.5. When you plug in 0.5 into this, you get f of x is equal to 1.5. 6 times 0.5 times 1 minus 0.5 is 1.5. And so f divided by g is going to be 1.5. So our constant is going to be m 1.5. So what this does is when you multiply g times 1.5, it goes up there. All right, so this is no surprise. This is very, very simple. But now the idea is I'm going to generate random uniform values. I multiply by that constant m, okay? And then we're going to accept only the values if the random u ends up less than kind of this ratio. Right? So I'm generating 100,000 values from the random uniform, and we calculate the ratio, which is basically just the red line divided by the blue line, okay? So right here, if I generate x equal to 0.5, I'm going to accept 100% of them. Okay? But then, say over here, if I generate x equal to, say, 0.8, okay? This is 1.5 and this is around 1, okay? So I'm only going to accept this with probability 2/3, okay? So I'm going to generate 0.8 sometimes, but I'm only going to accept it 2/3 of the time, okay? And then if I generate, say, x equal to, say, 0.99, right? I have an equal probability of generating 0.99 as I do 0.5, but I'm only going to accept, say, like 2% of those, okay? Right? Because in the F distribution, according to the red distribution, I shouldn't get 0.99 very often. Okay? So we're only going to accept that with a probability of that. So I calculate this ratio, right? I calculate, here's my proposed x value, whatever it is. We're going to calculate f of the proposed x. Okay, sometimes it's low, sometimes it's high. And then we're going to divide by m times g, right? G of the proposed x is 1. So m times g is just 1.5, right? So this part down here is just a constant, okay? This is a little bit silly, but this is just 1.5, okay? And then we're going to generate 100,000 random uniform values, okay? We generate the random uniform values here independently of the random uniform values that we generated over here, okay? Your proposed x that gets generated has to be independent of the u. So sometimes I see students will like set the seed to 1 here, generate using random uniform, and then they feel compelled to set the seed again, right? And if you do that, then the random uniform values you generate here will be like the same random uniform values that you generate here, okay? That's going to cause problems. So set the seed once at the beginning and don't reuse the same values, right? Generate a new set of random uniform values, okay? And then we're going to get a logical vector. If u is less than r over x, we've got true or false. So accepted is a logical true-false vector. And then basically I'm going to subset from all of the proposed x values. I'm going to subset some of them. I'm going to subset only the accepted ones. So the accepted x is going to be a lot less than how many I originally generated. I generated 100,000, okay? And I'm only going to keep basically this portion here. I'm going to throw away this stuff. I'm going to throw away this stuff. I'm going to throw away probably around 1/3 of my values. Okay, I'm going to throw away around 1/3 of my values. So out of 100,000, I'm probably going to keep something around 66, 67,000. And here is a histogram of the values I accepted. And we can see that the values I accepted, that histogram fits the theoretic probability of the data distribution quite well. And if I create an empirical CDF, it's kind of hard to see. So the theoretic is in red, and the empirical CDF is in black, and it sure looks like the empirical, the black CDF lines up very closely to the red CDF, all right? And we can see it's not perfect. It's not, well, I guess because I did the red line so fat, it fits entirely in it, but it's not, they're not exactly parallel This is truly an empirical CDF, and there's a little bit of variance there, okay, but it fits it quite well. Here's a little plot of what happened, okay? So here the horizontal position represents kind of the random value I generated, and then the vertical position is where that random uniform value, right? So I'm accepting based on the uniform value. And so I only accept if the uniform value ends up kind of lower than what the what that ratio ends up being, okay? And so we can see that the values that end up under the curve get accepted, the values that end up outside of it in red, those get rejected, okay? And so we can kind of see that, if I keep throwing random uniform values on the thing, then kind of the amount that's going to get accepted will just be those that fit in this distribution here. Is that all right? Oh, I'm going to run out of time. Okay, well, if we take and we say, okay, how many values did I accept? Okay, so out of the 100,000 values, looks like I accepted 66,658. So yeah, right around 2/3. And I proposed 100,000 values, okay? The theoretic acceptance rate is going to be 1 over m, right? So I have that constant m, I multiplied m times g. So the theoretic acceptance rate is going to be 1 over m. The reason for that, the reason why it's 1 over m, is because the original distribution's back here. The area under the red curve, it's a PDF, so it has an area of 1. The area of the orange curve, or in this case just the rectangle, also has an area of 1, right? So if you look at this area of this rectangle, area under the red curve, both of them have an area of 1. When I multiply one of the PDFs by m, its area is going to be m. Okay, so when I multiply the yellow line by 1.5, and I have this blue line, the area underneath the blue line is now m, okay, m times 1. It has an area of 1. So how much of it is covered by the distribution f? F has a distribution of 1, okay? F has an area of 1. The area under f is an area of 1. The area under m times g is m. So the amount that I'm going to accept is going to be 1 divided by m. So kind of the ratio between the proportion of m times g that's covered by f is going to be 1 over m. Okay, so this is my theoretic acceptance rate, 2/3. I think that makes sense. Okay, I guess we'll have to save the other example for later, and that's fine. We'll save that for Wednesday, because Monday we got the test. So we'll see you guys on Wednesday. Good luck as you study. This weekend I'll email out, I guess, a seating chart, so keep your eyes open for that. I know, it feels weird. I think it's going to be all like, we're going to be super spaced out because we can afford it. So probably like, it's going to be like every other row and probably like 2 or 3 seats between you and your neighbor, just to kind of reduce any possibilities of something questionable here. Okay. Oh, last view quiz answer, right? Letter A. A as in apple. A as in apple. All right. Have a good weekend, everybody. Good luck as you study. We'll see you guys on Monday. And yeah, have a good weekend.